In March 2025, Joel Zhang, a solo software engineer, set out to see if Google's top AI model could beat a game made for kids. Now, the game was Pokemon Blue, which came out in 1996, and Zhang built the system after seeing people online ask whether Gemini could play Pokemon better than Claude. Now, a year earlier, Google had released Gemini 1.5 Pro with a context window of about 1 million tokens. Google said it can now hold entire books, code bases, and work files all at once. So Zhang had a basic setup running in just 2 days, and on March 28th, he put it live on Twitch as Gemini plays Pokemon. On May the 2nd, after 813 hours, the AI managed to beat the game. Yet there was one time during the experiment that Zhang had to step in. The AI that was able to plan 150 moves through a maze got stuck in a small yard behind one of the game's gyms. The way out was just a gap in the fence, but the AI didn't find it. It walked in rings, turn after turn, while it told itself it was stuck, and Zhang watched for close to 8 hours. By then, its memory was ballooning, and it held each move, plan, and dead end from its past. Zhang said it had gone into a pattern repeating mode, and he ended up clearing its memory. On the agent's next try, it walked right out of the yard. Now, Google's own report also notes a similar trend, stating that once a model's context exceeds 100,000 tokens, the agent tends to revert to past actions rather than making new plans. And this failure highlights one of the great contradictions within large language models. The best and greatest models can hold vast amounts of text, but that can also lead them to replicate old moves, false ideas, and repeat bad habits. Long context helped Gemini to win, but it also cost the AI 8 hours stuck in a yard. Now, this definitely wasn't a clean lab experiment in any way, but still it raises a key question. Do large language models exhibit similar problems outside the context of games? When we give our business AI systems access to more abilities, more systems, more files, more rules, more emails, does more context end up making it work better? Or are our systems getting stuck in their own versions of that fenced yard? And that leads us to a 2025 research paper by Du et al. Titled "Context Length Alone Hurts LLM Performance Despite Perfect Retrieval." And this paper makes a bold claim that even though large language models can go through large swaths of text and find all of the important facts, when you ask it to reason over those facts, the answer accuracy goes down the more context that you give it. And to see why, the paper breaks down jobs into 2 different parts. The first is retrieval, which asks, can the model find the right facts within the text? The second is task completion, which asks, given that the model can find the right facts, can it use those facts to complete tasks? And what I found personally interesting is that a model can pass retrieval but fail task completion, which means it can go through a large piece of text and quote all the right rules and facts, and then in the next turn use those facts incorrectly. To explain the experiment briefly, researchers chose a task that a model could solve well and then injected additional context into the task. They tested 5 different models across 4 different types of tasks. Some of the models performed well, but others struggled. For example, Llama 3.18b was able to find the correct proof in 970 out of 1,000 tests, which is near perfect retrieval. Yet, as the context increased, its task completion fell by 24.2 points. The facts were there, the model found them, but as the context increased, it got worse at using those facts to answer questions and do tasks. That said, one interesting thing to note is that all the models didn't fail the same way. The 2 small open source models, which were Llama and Mistral, had the worst fails, while GPT-4.0, Claude, and Gemini did much better on most tasks. Now you might be thinking, of course, as the context increased, the answering got worse. You're basically just giving it unnecessary information, which increases noise. But the research team also considered this, so they replaced the injected context with blank spaces. The score still fell. Or maybe the model was focusing too much on the blank spaces instead of the facts. So they masked or hid the extra tokens from the model. The score still fell. Or maybe the facts themselves were too far apart from the question. So they ended up putting the facts and the questions side by side. The score still fell. None of these steps managed to fix the issue. The size of the context itself seemed to be the problem. And something to note though is that the researchers only tested adding up to 30,000 tokens, which could also explain why only the smaller models had issues. And I personally suspect is that if they tested close to 1 million tokens or higher, the larger models would also struggle. So what's actually happening here? Why do LLMs struggle with answering questions as context windows increase, even if they can perfectly find all the facts required? Now, the root cause of this may lie in how large language models are built and architected. Now, LLMs are based on attention, which is the way a model works out which parts of your input matter. Now, attention itself has a set pool, and each token must fight for a share of that pool. And there's a math step named softmax that assigns the share for each of those tokens. So when you add more tokens, you add more things that can claim a share. And tests have shown that when the input grows from 500 to 15,000 tokens, a model ends up spreading its focus over more text. The amount of entropy increases and focus decreases. Where you put facts in the context also play a role. Models do well when the answer is near the start or the end of a context, but do worse when it's in the middle of that context window, which is a pattern known as lost in the middle. It also adds noise, since facts that don't really help you to complete the task still fight with those key facts for that same pool of focus. So as this noise grows, the model can lose its grip on the facts that matter. Basically, the model's own past text lock it into a loop. Once a phrase or a move is in the context, the model ends up reading it again, and at the next step, often makes the same move it did. So now that we've talked about that, we were curious whether or not we could reproduce the paper's result on a smaller scale. Now, the paper tested things like math word tasks, multiple choice tests, and coding tasks. Now, those are useful, but will the same issues show up in work that looks more like a real office task instead of like these school-based tasks? So basically, we created a small set of tests ourselves on a very small scale. We based our experiments on simple accounting tasks like allocating payroll and coding bank transactions. And similar to the main experiment, we kept the facts and the final questions the same, but we varied the amount of additional input or context we provided. And we tried 3 different models: Mistral Nemo, Llama 3.18b, and GPT-4.1 Nano. For each model and task, we ran 5 trials for retrieval and 5 trials for task completion. And basically, we asked the same question. Can the model find the facts? Can it use the facts to answer the task? So we tried adding 30,000 and 60,000 tokens, and all in all recorded about 720 results. And the clearest result again came from Llama 3.18b. In one of the experimental sets, we asked it to retrieve all the rules on hours, pay rate, overtime. It was able to get that retrieval right all the 5 times. But then we asked it to calculate the pay using the same input, and all of the 5 answers were wrong, leaving the final score at 0 out of 5. So both in the paper and in our experiment, Llama was able to find all the important facts correctly, but it wasn't able to reason and complete the tasks at the same rate. Mistral Nemo also suffered, but not as badly as Llama. Its task completion score dropped from about 50% at 30,000 tokens to just 25% at 60,000 tokens. And in comparison, GPT-4.1 Nano was managed to pass all 20 long input tasks at both 30 and 60,000 additional tokens. Now that said, I want to be clear about what our test shows. Now we ran each model task only 5 times. With so few attempts, I probably wouldn't be comfortable concluding anything about these models, but I would say this is enough to show that it's at least worth it to take a look. Especially if you're building a production AI system yourself, you probably should determine and test your model's optimal context window for your business situation. Wouldn't our models do better if we gave it all the right information it needs? Maybe we give it more stuff like information about the business, about the client, about the project. We give it any and all rules required to complete a task. Well, maybe. And the first thing to really ask ourselves is, do we actually know if we're giving the models the right amount of context? And if we don't really know, it's probably worth setting up some sort of eval to test this on your system. And we can start with the main idea in the paper. So instead of asking a broad question like, did the AI get it right? You want to ask two questions. First, you want to ask, can the model find the facts and the rules it needs across that text? Basically, we want to create evaluations for retrieval. Secondly, we want to ask, can it use those facts within the context to give us the right answer? Basically, create evaluations for task completion. And we know from the research that these are actually two separate skills, and an LLM can be good at one and bad at the other, as Llama was in our test. And if you check only the final answer, sometimes you'll see that it's wrong, but you may not know why. So to build your own eval, start with a task that has a clear right answer, set up two evaluations. The first should include only the facts and the rules that it needs, and the second should include the types of text that your AI might have additionally, such as more rules, emails, notes, old files, context. You want to aim for the total amount of context tokens to be realistic for your system and your use case. And if the model can find the facts but starts to fail the task as the input grows, you've found your own fence yard. So if your eval shows that your system has this gap, you want to start with the obvious move, which is cut what goes into the prompt. Don't just add every single rule, email, context file just because you can. You want to use the data that's most useful for that one task and then leave the rest of it out. And if that's not enough, or if it's too hard to do that, you want to add a pre-processing step. Basically split every single one of these difficult tasks into two different steps. Step number one, find the facts. Give the model the full source, but tell it not to solve the task. Instead, ask it to relist all the relevant facts and rules. And step number two, actually do the task. But instead of using the large context, use only the relevant facts from the last step as the input. And if you're a developer, this is very similar to the plan-then-execute workflow you would find in tools like Claude Code, Codex, or Cursor. And that said, make sure you actually run an eval before assuming long context is the issue. Now, in our tests, even an older model like GPT-4.1 Nano was able to confidently pass every single test we gave it. My point is that you don't really know how your system behaves until you've run the evals. Which brings us back to Zhang and his fence yard. Now, what he did to fix this wasn't to upgrade to a smarter model or a bigger context window. Zhang instead improved his harness, so it summarized recent events and reset the context every 100 turns. Sometimes the answer to a stuck AI system isn't actually more information. It's less information, but better. So before you add another file, another log, another rule to your prompt, you want to ask if it is going to actually help the task completion. More context can make a system smarter, and sometimes it does, but you don't really know until you test it. And if you don't, you may end up with your own AI walking in circles endlessly, stuck in its own version of purgatory, refusing to just walk through the exit. Thank you for watching.